Did you know there's an entire master's level astrostatistics course available on GitHub for free? This is day 6 of learning computational astrophysics in 30 days. Today I move properly into frequentist inference. The basic idea is that you start with a load of noisy measurements, assume some model for which they came from, and then try to work backwards to find the most likely value of the parameters. So really there are two main questions. What is the best estimate and how uncertain is it? I started with maximum likelihood estimation. Likelihood asks, now that I already have the data, which possible parameter values make the measurements look the least surprising? To test this, I generated 1000 Gaussian measurements centered around a mean of 1. For every possible value of the mean, I calculated the likelihood of getting the data that I observed. Each measurement gives its own likelihood curve, and when you combine them all together, they form one much sharper peak. The highest point of that curve is the likelihood estimate. For Gaussian measurements with the same uncertainty, the maximum likelihood estimate should be the sample mean. I found the answer numerically and then compared it to the ordinary average of the data. These two results basically landed on top of each other. After finding the best value, we also need to find out how precise that estimate is. This is where Fisher information comes in. Very sharp likelihood peak means the data strongly prefers one specific value. A broad flat peak means lots of different values can fit the data almost equally well. So we want a sharp peak for a more precise estimate. Mathematically, the Fisher information is linked to the curvature of the log likelihood near its maximum. The more sharply the curve bends down, the more information the data contains about the parameter. So what I did was calculate the second derivative of the log likelihood near its peak to estimate the uncertainty. The prediction was pretty good as the estimated mean and the analytical mean matched perfectly. Finally, I used that uncertainty to build a Gaussian approximation around the maximum likelihood estimate. When I plotted it on top of the actual likelihood, the curves almost perfectly overlapped. In this case, that is expected because the original data was Gaussian, so the log likelihood already has the right quadratic shape. I also did some problems related to this, but you can check that out on my Jupyter notebook. See you next time.